So now for one of the more fun and useful things to do with the derivative. Find out where there's a minimum, a maximum, and in Math3C we can find saddle points. So you may remember in Math 3A, if you have a function like this, right here, the derivative equals 0. And there's a maximum point. Right here, there's a minimum point, and the derivative does not exist because that is a sharp point or a cusp. So you need to look out for where the derivative equals 0 and where the derivative does not exist. Furthermore, if you knew that the derivative equals 0 at a point, and you're trying to decide is that a maximum or a minimum, you could use the second derivative test, which says if the second derivative is negative, then it's concave down, in which case that's a maximum. If it's concave up, that means that the second derivative is positive, and that point down there would be a minimum point. Now in Math 3A, the closest we had to a saddle point would be y equals x cubed. So the graph looks like this. And at the origin, the derivative will equal 0. But this is neither a minimum or a maximum because it is concave down on this side and it's concave up on this side. So this we would just say is not a minimum or a maximum. But in Math3C, since we're dealing in 3 dimensions, check out that nice saddle. So right here, that's a saddle point. Because if you look at it this way, so looking at it this way, that point is a minimum. But if you look at it the way the person's legs go, their legs go like this, up here and then over the other side. And so going this direction, it's a maximum, and going this direction, it's a minimum. That is called a saddle point. Thanks, Google. Okay, so now for Math3C. First of all, we need to find the critical values. So that's like this part. Where does the derivative equal 0? Where is it that the derivative does not exist? But of course, we're going to have 2 derivatives because we would have a function of x and y. So we need to take the derivative with respect to x and also the derivative with respect to y. So there's going to be critical values, and that can happen in 2 ways, much like this and this. One is you take the derivative at some point a comma b, and it equals 0. Also, at the same time, the derivative with respect to y will also equal 0 at that point. If that happens, you've got a critical value. Then we'll need to figure out, is it a minimum, a maximum, or a saddle point? A second possibility is like this right here. And that is, if either of the first derivatives does not exist, like you've got division by 0 or it's somehow undefined, then that's going to be a critical value as well. Now we need to move over to this part, the analogous case or the analogous theorem for the second derivative test. And for that, you use the discriminant. So the discriminant is a little 2x2 determinant. So you take the second derivative of f with respect to x both times. Then second derivative f with respect to x and then y. And then y and then x and then y and y. Calculate that little 2x2 determinant. Now what do you do with that? So we assume we've already done this part. Then Since you've already done this part, you know the numbers a and b. So really, technically, this should say comma AB, comma AB, comma AB, comma AB. Okay, so if the d is positive, then there's two possibilities. You've got a maximum if the second derivative with respect to x each time is negative. So second derivative negative, that's like concave down, and that means maximum. Then there's a minimum if the second derivative is positive. Second derivative positive, that would mean concave up, and then concave up means that this is a minimum. And then finally, if d is negative, that means that you've got a saddle point. That is pretty much all of the theory in this section. Now we're going to move on to examples. So for example number 1, the function is x cubed plus y squared minus 2x squared plus y minus 7. First things first, take the derivatives, set them equal to 0. So the derivative with respect to x will be 3x squared. The derivative of this is going to be 0. This is going to be minus 4x. Now take that derivative and set it equal to 0. On the right side, I could actually factor out an x. So that would leave 3x minus 4. And then set this one equal to 0, you'll get x equals 0. Set this one equal to 0, you'll get x equals 4/3. Okay. Also, take the derivative with respect to y. So this will be 2y, and this will be 1. And then when you set that equal to 0, it's going to be y equals negative 1/2. So it has to be this and this. That means we actually get 2 points. So the critical points will be x equals 0 and y equals negative 1/2. Also, x equals 4/3, y equals negative 1/2. So there's something important happening at those 2 points. The next thing to do is take the second derivatives. So the derivative with respect to x 2 times. So take the derivative of this derivative, and that's going to be a 6x minus 4. Then take the derivative of x, and now take the derivative with respect to y. So I'm setting it up like this. So I'm going across like this, and then I'll do these guys. So right now I'm working on this one right here. Well, you take the derivative with respect to x, and now take the derivative of this with respect to y. That is 0. Now take the first derivative with respect to y, and take its derivative with respect to x. So the derivative of this with respect to x, 0. Now take the second derivative with respect to y each time. So the derivative of this with respect to y will be a 2. So the discriminant is going to be take 6x minus 4 and 0 and 0 and 2. Now you can either just do this with algebra, in other words with x in it, and later plug in these numbers, or you could plug in the numbers and then do the discriminant. You'll end up with the same thing. I prefer to just do it with x. That way I only have to write down this discriminant one time, and then I can stop saying the word discriminant. So the main diagonal is going to be 2 times 6x minus 4. So now I need to test each one of these points. So at the point 0, negative 1/2, d will equal, so that's basically just saying plug in x is a 0. So that'll be 2 times 0 minus 4, that equals a negative 8. And when you get a negative, that means that it's a saddle point. So x is 0, y is negative 1/2. And sometimes you'll be asked for the z value and sometimes you aren't. So I'm just going to go ahead and find the z value. So I'll take 0 and negative 1/2 and then substitute that back into the function. So x is a 0 and y is a 1/2. And x is a 0 and y is a 1/2. And I'm just double checking, did I type it in right? So 0 cubed, oh, I don't think I typed the negative, I think I typed the positive. So that's going to make a difference right there. Right there it doesn't make a difference because it got squared. Okay, so then the z value is negative 7.25. All right, that's one of them. That's this one. Now I need to do the discriminant again with this point. So then at the point 4/3, negative 1/2. So then d will equal 2 times, and then just plug in a 4/3 right here for x. So 6 times 4/3 minus 4. So that is, let's see, 6 will divide into that 2 times. 2 times 4 is 8. So it's 8 minus 4. So that is a positive number. The number itself doesn't even matter. What is that? That's 4, that's an 8. That is a positive number. So we have either a minimum or a maximum. So we're to this point right here. The d is positive. Now you need to look at the second derivative and see, is it negative or is the second derivative positive? And I mean the xx second derivative. So that was this one right here. So 6x minus 4. So the second derivative, when you plug in 4/3 and negative 1/2, will be 6 times 4/3 minus 4. So that is going to be, well, that's just this part in the parentheses. That is 8 minus 4, which is a positive number. And when you have a positive, that's like being concave up for positive second derivative, and that means it's a minimum. So then there's a minimum when x equals 4/3, y equals negative 1/2, and z equals what? So substituting this into the calculator. So 4/3 gets cubed, and plus the negative 1/2 gets squared, minus 2, and then x gets squared. 4/3 gets squared. and then plus the y, which is negative 1/2, and minus a 7. And then that equals negative 8.435. Okay, so now we're done with the first example. Let's go take a look at the graph and see if these two seem correct.
Hey, how's it going? So take a look at this graph, x cubed plus y squared, etc. And looks like a sheet that's, a sheet of paper that's sort of crumpled a bit. Anyway, I need to sort of zoom out to see better. Oh, there, that's better, I can see. So it looks like there's a minimum right here, and it looks like this is going to be a saddle point, because remember we got a saddle point and a minimum? So this point right here, so this is like the saddle. So this part says that is a minimum. And then if you follow it this way, right here, it's saying that it's a maximum. So that should be the saddle point right there. So this one would be the saddle point, A, yes, just like what I was saying. So that one looks great. That's the saddle point. Then, did I get the minimum correct? So the minimum should be right there. And point B, could I get a drum roll, please? Yes. Thank you, thank you. Hold your applause till the end, please. All right, let's get back to it.
Well, example number 1 covered most of the ideas. There's just one other little detail. Suppose this was Math3A and you had this function. You would take the derivative and find out there's a maximum right here. You'd take the derivative, set it equal to 0, you'd find out there's a minimum right there. But then if they said, I want you to consider this function on the interval from -1 to 2, well, when you plug in 2 to the function, you'll find out that there's a maximum right there, even though we did not find the derivative equals 0. And when you plug in -1, you'll find out that there's a minimum right there, even though the derivative did not equal 0. So when you're given an interval, then you need to check the endpoints. That's what we're going to do on this example right here. So for example number 2, the function is equal to 2x squared plus xy minus y squared. And then we're going to go have x go from -2 to +2, and y is going to range from -3 to +3. This part we do later. Right now we need to start off like usual, and that is take the derivative with respect to x. So this would be 4x. The derivative right here with respect to x is going to be 1 times y, and then set that equal to 0. Since there's 2 variables, I cannot solve for them. I need another equation. Oh, I know. What about the derivative with respect to y? That would be 0. This right here would be a 1 times x, and then minus 2y. And set that equal to 0. And now we have 2 equations with 2 variables. So right here, I could move the 2y to the other side, and x is equal to 2y. Oops, 2y. X is equal to 2y. And then if x equals 2y, I could plug it in right there. So this says 8y plus 1 more, in other words 9y equals 0. So that means that y equals 0. Plug that in over here, and it's going to say x equals 0. So the only critical point that we get is 0, 0. So is there a minimum or a maximum? The second derivatives will help us out. So for this one, we're looking for the second derivative. So take the derivative of this with respect to x. That's just going to be the number 4. Now take the derivative of this one with respect to x. That's just going to be the number 1. Now take the derivative of this one with respect to y. That is just going to be a 1. And now take the derivative of this one with respect to y. That's going to be a negative 2. So this would be negative 8 minus 1. So that is a negative number, which means there's a saddle point. So saddle point when x equals 0, y equals 0. And this one, if x equals 0 and y equals 0, then z equals 0 also. So there's a saddle point at the origin. Now, if we didn't have this, we would actually be done with this one. So now we need to deal with this. So that's saying, if you want to look at it visually, it's saying x is going to have to range between negative 2 and positive 2. Y is going to have to range between negative 3 and positive 3. And now we need to test this line right here. So this line right here, so what's happening to the function if you're walking along this line and then you're looking up to see the function? What's going on? Well, this line right here is the line x equals 2. So that means just go to the original function and x has to be a 2. So this will be 2 squared 4 times 2 is 8. This has to be a 2, so that's plus 2y, and then minus y squared. So we just get a function of y, since x is a constant 2. Now take the derivative to find out where there's minimums and maximums. So the derivative would be 2 minus 2y. Set that equal to 0. Could even factor out a 2. And that means that y equals 1. So at y equals 1 and x equals 2, there's something important going on. So x equals 2 and y equals 1. So then what's going on? Well, you might think, well, let's go ahead and do the discriminant. But the thing with the discriminant is you have to know that the first derivative equals 0. So in order to be using the discriminant, you have to know that the first derivative equals 0. I mean the first partial derivatives. And when we did the first partial derivatives, the only numbers we got are 0 and 0. So you can use the discriminant if you're talking about 0, 0. This is not talking about 0, 0, so we're going to have to figure out something else. So at 2, 1, what does the z value equal? So f of 2, 1 equals 2, and then x is going to be 2 squared plus 2 times 1, so I'm just plugging it into the original function, minus 1 squared. So in other words, the z value is equal to, this would be 4 times 2 is 8. This would make it 10, this would make it 9. The z value is 9. Then what if you were really close to that point? Now I know x has to equal 2, but what if I went, so this is the point that we're talking about right now. So what if I made the y value like 1.1? What's going to happen to z? So leave 2 alone and use 1.1. So what's happening there? So it's going to be 2 and then x is squared, so 2 squared, plus the x times the y, and then minus the y squared. So how does that affect the z value? So this is going to be 8 plus 2.2 for that part, and then minus 1.1 squared. So it turns out that it's smaller. So if you move away from the point, it's going to get smaller. That means this one is a maximum. So then I can label, I've got a maximum at 2, 1, 9. Okay, so I don't think I'm going to do all of them, but I'll do one more. So you have to do the same thing for all 4 sides of this rectangle. I'm going to do this one right here. So what about when y equals 3? So the case where y equals 3. So that means you can go back to this function and plug in a 3 right here and a 3 right here. That makes it a function of just x. So it's going to be 2x squared plus, this is going to be 3 times x, and this is going to be 9, so it's minus 9. And then to find minimums and maximums, take the derivative, which is going to be 4x plus 3. Set that equal to 0 and solve for x. So x is going to be negative 3/4. And a negative 3/4 is within this range, so it is a possibility. So what's the at x equals negative 3/4 and y equals 3, then what happens to the function? So that's 2 times negative 3/4 gets squared plus, so I'm just substituting in the function right now, the x times the y minus the y squared. So that is the value at that particular point. How much is that? Negative 3/4, trying to type too fast, gets squared. And then it would be minus, this would be minus 9/4, and then minus 9. So negative 10.125. So the z value equals negative 10.125. Once again, we cannot use the discriminant, so you have to pick a point that's close to this. This is saying no matter what, y has to equal 3. So then pick a point close to this. So this equals negative 0.75. I'll test a point like negative 0.7 and 3. What does z equal? So it's going to be 2 times x squared plus the x times the y minus the y squared. So 2 times negative 0.7 is squared, and then this would be minus a 0.7 times a 3, and then minus a 9. It equals negative 10.12. So this is actually smaller than this. So this is actually a minimum. So then there's a minimum, and then x was negative 3/4, y was 3, and then the z value is negative 10.125.
Okay, here's where the 3D graphing really helps. I'm confident in my math, but I really like to visualize what's going on. You may have heard me say that before. So if you look at the origin, let me zoom in a little bit. Well, it doesn't really change much. So going this way, it looks like the origin is a minimum. But if you view it this way, then it looks like the origin is a maximum. So that is a classical saddle point. All right, so that one's good. Done with that one. Next, remember we did the boundaries. So when x equals 2, so I'll just put up a plane, x equals 2. And you could see right up here where it's slicing the red function, right up here, it looks like there's a maximum. So did I get that point right? So that was 2, 1, 9. Yes. So that's the maximum up there at the top. Is it at the top? Yeah, well, GeoGebra, you can see it's sort of jagged up there. I think it's just not graphing extremely accurately. Also, I think it depends on the angle you look at. Anyway, so this is looking pretty good. Then y equals 3. So for that, it slices it, and you can see there's a minimum down here. I wonder why it's not smooth right now. Okay, then point C should be down there at the bottom. That should be the minimum. Yes, got it.